All right, welcome back, everybody. Today we're going to be doing section 7.5, which is all about simple harmonic motion and combining waves. This is actually one of the cooler sections because there's a lot of stuff that you will use later on in your careers. So I'm excited to introduce you to some of the basic ideas there at least. Um, so yeah, let's get started. Let's take a look at the slides and see what's in store. Okay, so the first thing we're going to do is we're going to develop some intuition for what simple harmonic motion is and what it means. Then we'll get the definition. Then we'll talk about damped harmonic motion. Then we'll talk about graphical addition and combining waves. And then at the end, I'll talk about some ideas that are on the mathematical horizon. So, like I mentioned early on in the course, I doubt anybody remembers because it's been, weeks and months. But you should always be asking, why am I learning this? Why do I care about this? Why is this important? What could I use this for? You should demand meaning and substance from these types of ideas and the classes that you take. Um, the nice thing about math to me is that pretty much everything that you all are learning, you can use later on. And even if you don't use it, it gives you this incredible insight into how other people would use these ideas to build things in the real world. I don't just mean like physical buildings. I mean just building ideas, abstract constructs, all those things. So today, this section is one of those sections where you get a little bit of a taste of that in a really interesting way. All right. So, what's the intuition? So, basically, almost any oscillatory behavior can be described in terms of sinusoidal functions. And this is something that I mentioned previously in the course as well. Um, anytime you witness something oscillating or bouncing back and forth or moving in a circle or any kind of like wave pattern, the way that we describe it mathematically is with sinusoidal functions, sines and cosines. So simple harmonic motion is a form of oscillatory behavior, and a lot of wave-like phenomenon exhibit this type of motion. For example, the swinging of a pendulum. Here are some classic examples, right? Swinging of a pendulum, sound waves is a big one, light waves, ocean waves, vibrations, etc. All of these things obey simple harmonic motion, or they exhibit simple harmonic motion. Um, the example we're going to use today to gain some intuition is the bouncing of a weight hanging from a spring. So just imagine that a spring, or I'm sorry, imagine a weight is hanging from a spring, right? And then you let it drop and it kind of bounces up and down. We're going to see an animation in just a minute here. But the vertical displacement of the weight follows a sinusoidal pattern. So that spring, even though it's moving just back and forth, it's following simple harmonic motion. The motion can be described with a sinusoidal function. So what's cool about this stuff, and what I'm hoping you'll be able to take away from today's lesson, is that you have all of the foundational skills that you need to explore and describe such behavior. So anytime you're out in the wild doing anything, I don't mean like the woods, I just mean like when you're out in your life exploring, looking around, thinking about stuff, look for vibrations and look for waves and look for simple harmonic motion. And what I want you to realize is you now have the ability to perfectly describe that motion using mathematics, in particular trigonometry. So we're going to see a little bit of that today. So here is the definition, and this is the most general definition. And for those of you that go on to take a course in differential equations, which I hope is many, if not all of you, you will actually show, or I should say, you'll start with this definition and you'll derive the model for simple harmonic motion that we're just going to take as a definition in a moment. So, what is simple harmonic motion? It's a type of vibrational motion in which the acceleration A of an object is directly proportional to the negative of its displacement d. More specifically, this equation right here is what describes simple harmonic motion. K is what's called the proportionality constant. It's just a constant of some sort. But what this equation is telling us is that the acceleration of the object is proportional to its displacement, d, but it's proportional to the negative of its displacement. And we'll talk about this again in just a moment when we see the animation. But this is how simple harmonic motion is defined most generally. Now, because of that, we have this really interesting theorem that categorizes this motion. And this is the result that you would prove in a course on differential equations. We're just going to take it as a theorem for now. But it's this. So let A, B, phi, and omega be constants with omega greater than 0. Then an object that moves on a coordinate axis, either the x or the y, whichever axis, so that the displacement d from its rest position at a time t is given by this function, is an object that moves with simple harmonic motion. So let me restate that in a less wordy way. What this means is if your object obeys simple harmonic motion, it has that behavior, then this is a function that will describe that motion. That's really all it means. And hopefully this formula looks very, very familiar. You probably remember it from earlier on in the course, right? Because this is just the general form of a sinusoidal function. And what you had to do in the past, and what we'll do here as well, is you had to essentially find values for A, omega, phi, and B. And it's the same thing. So this is the exact same thing, but now what we're saying is that you can use this to model all sorts of different types of behavior. In particular, you can model simple harmonic motion. So let me emphasize some other little bits here. First thing, if you remember, the amplitude is the absolute value of A. The period is 2 pi over omega, and that's because the period of the cosine function is 2 pi. The phase shift is phi, and then B is going to be the resting position of the object. So that's where the object would settle and come to rest. All right, so let's talk a little bit more about this formula and what we've got here. This formula differs a little bit from the one that is in the book. So the book actually just gives you two versions of the formula without some of the bells and whistles, you could say. But you don't need two different versions. You just need to understand this little bit right here. Sine and cosine are just phase shifts of one another, right? And in particular, we have this relationship. We saw this much, much earlier on in the course. So what this means is that you can describe your simple harmonic motion using either sine or cosine. It's really your choice, right? Sine and cosine are kind of like the same function, quote unquote. They just differ by a shift. So depending on the context of your problem, that's going to determine if you want to choose cosine or sine. And I'll address this in the example that's coming in just a few minutes here. So long story short, you can choose to use sine or cosine, whichever you want to use. And the context is what makes you, or the context is what informs which one you should choose. Now, phi, so phi is actually determined by the initial position or the displacement and the velocity of the object. So more specifically, if we let d sub 0 represent the initial displacement and v sub 0 represent the initial velocity, then the number phi, that phase shift, has to obey this equation. Basically, v naught divided by omega times d naught. So in other words, you can solve for phi using the inverse tangent function, and you get this. That's the idea. Um, Now, the important note here is right at the bottom. If your initial velocity is 0, then that means that the phase shift is 0. So that's one thing that can make this a lot easier. And the book actually does not address this point at all. But essentially, if your initial velocity is 0, which it is for a lot of applications, then there is no phase shift. But as you could imagine, a lot of times in nature or just what you want to explore, your initial velocity may not be 0. It could be anything, right? It could be any real number. So generally speaking, if you needed to come up with a sinusoidal model for simple harmonic motion and the velocity was not 0, you would use the initial velocity was not 0, you would use this formula for it. Okay, so now let's take a look at this spring example to get some more intuition. You can click on this link as well. This is a hyperlinked clickable word or pair of words, and it'll take you to a really nice animation that's just straight from the Wikipedia page on simple harmonic motion. I'm going to pull it up here right now. Here we go. So this is showing you how simple harmonic motion is connecting to that sinusoidal function that we just looked at. So right over here on the left, where you see the weight bouncing up and down on a spring, that's the motion that we want to describe. So you can see that there's like a red box, that's the weight. The green dot in the middle of the box, that is the center of the box, and that's what we're going to use to track the motion. But as you can see, like the spring goes down, it reaches a minimum point, and then it shoots back up and then it reaches a maximum point, and then it falls back down, and it reaches that minimum again, and then it moves back up, back down, up, down, up, down, and so on, right? So we're assuming that there's no friction, we're assuming there's no air resistance, for now at least, but this is what simple harmonic motion looks like. And if you remember the definition of that motion, it was saying that the acceleration is proportional to the negative of its displacement, right? So if you if you look at the spring, when it reaches the minimum, when it reaches the bottom of that period right there, the next thing it does is it shoots back upward. So it accelerates in the opposite direction that it was going, right? So the acceleration is essentially decreasing as it falls, and then it increases as it goes up. So what's happening is the acceleration is proportional to the opposite, the negative of the displacement. That's what's going on. So what it turns out is that when you have that type of relationship and you solve that differential equation, because acceleration is actually the second derivative, which is something you'll learn about in Calc 1, when you solve that differential equation, you get sines and cosines as your solution. Now, over here on the right, this is what's called the phase space. And again, this is something that you'll explore more in a class on differential equations, but the phase space is basically giving us a visual interpretation of what the motion looks like circularly. So as that green dot goes around and around and around the blue circle, each point on that circle represents a specific state of the system that's going on the left. So you can see that, for example, when the circle is there on the left and moving downward, the spring is also moving downward. But when the circle is at the same height but on the right, sorry, the green dot, when the green dot is on the right, it's moving upward. So you can model this behavior. Oh wait, I'm going the wrong way. Wait, am I? There we go. So you can model this up and down bouncing behavior using a sinusoidal curve, a sine or a cosine or something like that. Here, the y-axis is indicating the position of the object, which is labeled there on the picture. And you can see that with the spring, right? The green dot keeps moving up and down, so the position is perfectly mapped onto the y-axis. And its velocity is mapped on the x-axis. And you can see how the velocity basically travels from negative to positive, negative to positive. The velocity is zero right when you're on the y-axis, right? When x is zero, you're on the y-axis. Well, the velocity is zero right at the bottom and the top of that period because the object is not moving up or down anymore. Its velocity goes to zero and then it changes direction. So it's like, positive velocity as it goes up, and then it kind of rests for an instant, and then goes down, negative velocity, and then it rests at the bottom for an instant, and then it goes back up. So, again, this is a picture that you should stare at and think about and try to make deep sense of because this is essentially how you encode all of simple harmonic motion. And there's an incredible amount of research involved with this stuff, and an incredible amount of discovery that you can make still just by knowing these basic ideas. So, this is one of the reasons I'm excited to talk about it today. Uh, all right, so let's go to, oop, that's the wrong one. Where is it? Where is it? Ah, here we go. Okay, so let's try to do an example. Oh, sorry, I forgot. There's one more definition before we do the example. Um, so the frequency of an object. So if your object is in simple harmonic motion, the frequency is the number of oscillations per unit time. So in other words, it's just how many times it bounces back and forth per minute, per second, per hour, whatever you choose to be your time unit. Now, remember that the period of the sine or the period of a sinusoidal function is given by 2 pi over omega, right? Well, the period is the time required for one oscillation. So if you go back and you like dig into that old idea, that's what the period is, the time required for one complete oscillation to occur. So that means that the frequency is just going to be the inverse of 2 pi over omega, the reciprocal, right? So the frequency is omega over 2 pi. And that's pretty much it. So you know what the period is. The period is 2 pi over omega. So the frequency of the object is the reciprocal of that result, omega over 2 pi. And we're assuming omega is zero here just for convenience. All right, now let's look at an example. So here's a classic example with the spring. Um, Suppose we got an object attached to a coiled spring and it's pulled down a distance of 5 inches from its rest position and then released. So you release it and it shoots up and then it falls down and shoots up and falls down. If the time for one oscillation is 3 seconds, let's develop a model that relates the displacement d of this object from its rest position after time t in seconds. And we're going to assume there's no friction. Friction and air resistance, all those things, they make the problem naturally much more complicated, but that's what you will study in your later courses. Well, in your later courses, they'll be like, hey, remember learning about that simple harmonic motion? Well, what if there is air resistance? How does that affect the problem? Or what if there is some other friction involved with the spring? How does that affect the model? And what could you do with that model? So that's what you're all going to do later. So that's cool stuff too. But for now, we're going to make it easy. We're going to assume there's no friction, there's no air resistance, just simple. Pretend the spring would bounce up and down forever, forever and ever and ever. Okay, so here's how we're going to start. The initial displacement coincides with the low point of the motion, right? So basically, you pulled the weight down to the bottom, and then that's what you're going to call the initial displacement. So the initial displacement is -5, right? And because the initial displacement is occurring at one of the extrema of this motion, it's occurring at the minimum or the max. In this case, the minimum. Cosine is the more convenient function to use. And the reason is that, remember, cosine, when t is 0 or when theta is 0, cosine is already at its peak. So what I mean is, if you think about the graph, let me do this here. Think about the graph of cosine, right? It starts up here and goes down. So in particular, at time 0, it's at an extreme of the motion. Well, that's exactly what we have in our situation right now. At time 0, we're at one of the extremes. We're at the low point. That's why cosine is a good choice to use instead of sine in this case. Okay, so we'll use cosine for this. Now, the other thing is we know right away that b is 0. So the initial position, the rest position of the object is 0, right there. So there's no vertical shift going on that we need to account for. Then we know that the initial displacement is -5. So that means that that factor of a, the signed amplitude, is going to be -5. Also, we know the initial velocity is 0, so there's no phase shift, or the phase shift is 0. Remember, when we pull the weight down, when we're holding it, at that moment, right before we release it, the velocity is 0. So the initial velocity is 0. We don't have a phase shift, so phi is 0. Next, we are also told that one oscillation is 3 seconds. So that means the period is 3 seconds. And so since the period is 3 seconds, we get this equation, which lets us solve for omega. So now we have all the pieces. We have A, we have B, we have omega, and we have phi. And we figured out that we were going to use cosine to model this function, or to model this motion. So this is what we get altogether. The displacement in terms of t is going to be -5 cosine of 2 pi over 3 t. And that's it. So what this function gives you is it gives you the displacement of that object hanging from the spring at any time t. And that's the idea. That's the idea. Pretty cool, huh? I think it's pretty cool. Okay, now that we know about simple harmonic motion, we need to talk about damped harmonic motion. So speaking more realistically, most physical phenomena are affected by friction or some other external force, right? It's not that that spring will just bounce forever in quote unquote reality. So oftentimes simple harmonic motion is just not appropriate to describe the behavior. It is appropriate to describe certain attributes of the behavior, but it's not enough to encapsulate the entire behavior itself. So the thing is that when you have other forces like friction, air resistance, they remove energy from the system, and that causes the motion to dampen. In other words, because of that friction, the oscillatory behavior that you're witnessing is going to decrease and diminish over time. Oh yeah, so here you go. So returning to the spring example, if friction or air resistance is involved, it causes the displacement of the object to decrease over time. And that's an attribute of the motion that is not encapsulated in simple harmonic motion. So that's one of that's one of the things we wish we could remedy a little bit, right? So it's like we've got a good model for things that are bouncing, vibrations, wave-like patterns. We've got a good model for that. But a lot of times it doesn't just stay that way. A lot of times the bouncing will actually diminish. So this is a picture of what damped harmonic motion looks like. So damped harmonic motion, it still involves a sinusoidal factor because there's still an oscillation occurring. So still involves a sinusoidal factor because oscillation is occurring. So anytime you're witnessing oscillations or you see oscillations, there's going to be a sine or a cosine involved in some way. But to get damped harmonic motion, there is an additional damping factor, and that's what we're going to use to account for the damping. Um, so the other thing is this, the period of the oscillation is affected by the damping. So a good example that I like to think of when I try to make intuitive sense of this is an air hockey table. I'm not sure if you all have ever played air hockey before, but if you have, or if you haven't, you should go play it at least once. It's a really good opportunity to see this kind of damped oscillation. But it's a good example because there's very little friction with an air hockey table because the puck is floating on a bed of air. So if you've played air hockey, you might have noticed that sometimes if you basically try to pin the puck against the side wall with the paddle, then it'll bounce back and forth between the wall and your paddle, and the bouncing will get faster and faster until it basically stops as you pin the puck to the wall. So what happens is, I'll try to like indicate it sideways here. Oh, I'll do it like this. Here we go. So what happens is when you pin the puck, it goes like like that. So you get this damped harmonic motion. So the puck, as it bounces back and forth, it's following simple harmonic motion. And so if there was nothing to prevent that, it would keep going back and forth. But that's not what really happens. So when you start to pin it, when you apply an external force, it bounces back and forth, but then less so over time until there's no bounce, right? No bounce at infinity. It's just kind of pinned. So this is a good example of what we would like to describe. So how can we describe such behavior? How can we describe something where there's an oscillation, but there's also a dampening factor involved? Well, this is how we're going to do it. So what happens is when you have damped harmonic motion, the oscillations are enveloped between two exponential decay curves. So enveloped between two exponential decay curves of this form right here. So this is just an exponential function. If you remember working with it in the past in pre-calc or algebra, that's really just what it is. It's a times e to the negative lambda t. This little letter right here, this is the Greek letter. That's the Greek letter lambda. And this is an exponential decay curve because you've got this negative coefficient right here, or this negative sign right here. So what that means is you're going to have exponential decay. And in essence, that is what is happening with these right here, these two curves right there. So the top curve is actually y equals a times e to the negative lambda t, and the bottom one is y equals negative a times e to the negative lambda t. And so those are the curves that are those curves, the pair of them is sometimes called the envelope because the oscillation is literally enveloped between these two curves. These curves are also known as bounding curves. There we go. They're bounding curves, and how do you determine what these curves are? You look for all the local maxima and minima of the sinusoid. So maybe I'll emphasize it right here. Go back to the pen. Come here. There we go. So this point, this point, this point, this point, all those points that are on the top right there, those are going to determine the upper bounding curve. And in this case, they're going to follow an exponential decay curve. You can do the same thing for the lower bounding curve. So like right here, right here, right here, right here, and so on. So those points that are below there, those are going to determine the lower bounding curve. That's how you would do it. So yeah, so now let's take a look at the actual model itself. Here we go. So here's damped harmonic motion. The displacement d of t at a time t of an object exhibiting damped harmonic motion is given by this function. There it is. um, Lots of stuff is still the same. Absolute value of A is the initial amplitude of the envelope. Lambda is the decay rate. The period is 2 pi over omega. The phase shift is phi. B is the initial resting position of the object, and so on. So everything is very, very similar to what we've seen before. The only difference is now we have this additional decay factor involved. So let me see what I have here. Yeah, exactly. This is where things can get really fun because whenever you look at these types of functions or these types of models, you should take to heart that each piece of it is representing an attribute of interest or it's representing something intuitive. So, like I say with this first point, the sinusoidal factor is precisely what encapsulates the oscillatory behavior of the motion. So, this piece right here, this cosine function, this is the part of the model that is specifically identifying and describing and encapsulating the oscillation, the bouncing. So this is like the bouncing. When you look at this, you can think of this as the bouncing, right? That's how we describe the bouncing part. Now, how do we describe the dampening part? Well, we're going to multiply that bouncing by a decay factor. Right. Here, I'll use green, right here. So A times e to the negative lambda t, that's a decay factor. So what does that part of the formula represent? What does it describe? It specifically describes the dampening behavior. So yeah, like I say down here, that leading factor encapsulates the dampening or decaying behavior. So what you can do is just by looking at this function, looking at the formula for it, you can see that it's an oscillation that's being dampened by an exponential decay curve. That's what those two colored things represent. And I encourage you to try to develop this intuition for any formula you've ever seen in your life because they've all got something intuitive for them, something intuitive going for them. You can make sense of it in a meaningful way. And what we're going to see at the end of this section when we do the graphical addition is we're going to see more of how you can intuit what these functions look like and what they're doing. All right, so let's just do an analysis here. So let's analyze the damped vibration curve given by this function. And what I mean is, oh, and t is greater than or equal to 0, so we'll keep everything positive. What I mean is let's just look at what's going on, let's explore the behavior, see if we can find the equations of the bounding curves and so on. All right, so the sinusoidal factor here is just cosine of t, and we're very, very familiar with cosine of t. Cosine of t is exactly the same cosine of t you've been working with since week 1, right? It's just cosine. The dampening factor is given by the leading factor right here, this piece, right? So e to the negative t over pi. And if we rewrite it in terms of the general formula, we get this. And so now that it's in terms of the general formula, or it's in the form of the general formula, you can see that the decay rate is 1 over pi. So this is saying how fast the oscillation is going to decay. Now, moreover, there's this really important calculation right below this like string of equalities and inequalities. I'll get to this in just a second here, but this type of thing is exactly what you're going to see a lot in Calc 1 and Calc 2 and Calc 3. So I encourage you to get comfortable with absolute value soon because you're going to use it a lot in Calc 1, 2, and 3. But if we look at the absolute value of the displacement, we can use an important property of cosine to figure out what those bounding curves are going to be. So if we take the absolute value of the displacement, we're going to get this right here. So just absolute value of that formula. Now, because absolute value of a product is equal to the product of the absolute values, we can rewrite this expression like so. And this is where we're going to use an important property of cosine. Now, you probably don't remember, but I've said it a few times over the course of this course, but we really, really, really love cosine, and we really, really, really love sine, and we really, really, really love arctangent. And the reason for that is because those functions are bounded. So cosine of t is a bounded function. It goes no higher than 1, and it goes no further down than -1. It's a bounded function. So in particular, its absolute value is less than or equal to 1. So this thing is less than or equal to 1, which is great. So now we can essentially kind of eliminate the oscillation for a minute here. If we're just thinking about maxes and mins, we can drop the oscillation entirely, and we get this. We get that, where is it? Maybe I'll say, I'll just go back to here. So the original displacement has got to be less than or equal to the absolute value of this, right? But that's an exponential function. So exponential functions are always positive unless they're intentionally shifted downward. But this is a positive function, so the absolute value of it is just going to be the function itself. And so what we get is this result. Let me emphasize it here. We've got that the absolute value of the displacement is less than or equal to this exponential function. And then if you use the definition of absolute value, what that gives you is this result right here, which we actually saw already when we were developing this theory. So this just says that the displacement is sandwiched between those two upper and lower bounding exponential decay curves. That's what this inequality says. The displacement is trapped between the bounding curves. So there you go. And I mean, it's really just all right there in front of you, right? Even when you just look at the original formula, you can see what the equation of the bounding curves is going to be because of this structure. It's really, really nice. So let's look at it pictorially. Let's see what's actually going on. So the black curve that you see here, that's just the standard cosine curve, cosine of t. The blue curve is what we get when we apply the dampening factor of e to the negative t over pi to it. So what's essentially happening is this. Let me grab my highlighter. We're taking this curve and we're applying a dampening factor to it. And when we do that, it becomes this curve right here, the blue one. The two pink curves, those are the upper and lower bounding curves. So you can see those right here. Where is it? Yeah, right here and right here, just like we figured out on the previous slide. So that's the envelope. The envelope is the two red curves that are sandwiching the cosine curve in between them. And that's how you get damped harmonic motion. Pretty cool stuff, huh? I think it's pretty cool. Okay, now that we've got this idea, we can talk about graphical addition, which is kind of fun. If you've never seen this before, this is something that can really, really change the way that you do algebra. So one thing I want to say here, it's not on the slides, but there's an intimate connection between algebra and geometry. And an important skill to develop when you're going through your math courses so that you can apply it later is to be able to pass between the algebra and the geometry. So we've actually been doing that this whole lesson so far. So we were looking at these functions, looking at these formulas, and then asking ourselves how that would affect the graph and going back and forth, right? With the oscillatory factor, the dampening factor, we can pass between those models and the pictures, the graphs. So we can do the same thing with graphical addition. So like I say here, in the previous example, in the previous exploration, we saw how a scaling function, in particular this, affects the graph of a sinusoidal function. And this made visual sense because the scaling function alters the vertical height of the graph. And we've seen this before. So we explored this back in section 1.5. So in section 1.5, that multiplier in the front, that coefficient in the front of your function, gave you a vertical stretch or a vertical compression. So the only difference between what we saw back then and what we're looking at now in this section is back then, everything was a constant, right? So A was a constant. But now what I'm trying to say is that you don't need that scaling factor to be just a constant, like 2, 3, or -1/2 or whatever. It could actually be a function in and of itself. You can talk about a scaling function. And that's what I'm saying right here. So instead of it being determined by just a constant, now it's being determined by another function. So what we've seen so far in this section, in these examples, is this. This was our scaling function. So maybe now you can go and like play with that idea. Open up Desmos and go and try to basically come up with a sine function or a cosine function and then just multiply it by different functions and see how that affects the graph. So what we're going to do now is we're going to do something similar, but we're going to use addition. And we're going to see how to get some visual intuition for the sum of two functions. And how are we going to do that? We're going to use what's called graphical addition. Graphical addition. So here's how we do it. First a bit of motivation. So sums of functions appear in tons and tons of applications. What I mean is a lot of times when you're exploring or investigating or doing some research, you will come across a point where you need to add two functions. Doesn't seem too far-fetched, right? You're going to have to add two functions. A good example and a very, very intriguing example I find is if you have two tones, so if two sound tones are played, then the sound produced is, if you play them at the same time, the sound produced is the sum of the waves produced by the two tones. So if you've got a tone that's like E and another one that's like E, and you wanted to know what would happen when you played them both at the same time, how would that sound? E, I can't do it at the same time. The sound that it produces is quite literally the sum of those two waves, the sum of those two waves. So we can make really good intuitive sense of that by using graphical addition. So here we go. So if f and g are two functions defined on the same domain, then the y coordinates of their graphs are just these. This isn't anything new. This is something you've seen for a long, long time. Basically, you map the outputs to the y coordinates. So what that means is that if you want to find the y coordinate of the graph of the sum of those two functions, the y coordinate of the sum of those two functions is just going to literally be the sum of the outputs of those two functions. So in other words, what this means is if you want to know where the y coordinate of that sum will be, take the y coordinate of f, the y coordinate of g, add them together, and that's the y coordinate of the sum, right? I feel like this almost feels like a more complicated way of saying something that you already know. But if you haven't done this graphically, you're about to learn something pretty cool. So graphically, what this addition corresponds to is adding the signed length of the line segment connecting the points x comma 0 and x comma f of x to the signed length of the segment connecting the points x comma 0 and x comma g of x for every single x. And we're going to do an example in just a minute. So I know there's no pictures yet, but pretty much if you look at the y, like you look at the vertical displacement of one function at a point and you look at the vertical displacement of the other function at that point, you're going to add those two together. And when you add those two together, that's going to be the vertical displacement of the sum. Not too bad. All right, let's see an example. So let's try to graph the function h of x equals x plus sine of x by writing it as a sum of two functions and then using graphical addition. So here we go. Here's what it looks like graphically. So I called the function x, f of x, and then I called the function sine of x, g of x. And then they're both graphed right here, both graphed right here. And then I think what I'm going to do here is I'm going to pause for a minute. I want you to look at both of these pictures and just think about how you would add the vertical displacements at each point. So think about it for just a minute. All right, now say something out loud. What were you thinking in your head? How do you feel like you could graph the function h of x by adding those vertical distances? All right, now let's try to do it together. And I'm gonna take a decent amount of time to do this. This is precisely what you would do at home if you were doing this on your own kind of thing. But quite literally what I'm gonna do is I'm just gonna measure distances and then add the line segments up. So I'm gonna zoom in a bit here. And okay, what I'll start with is, I'll start over here, but then I'll go to a more interesting part of the graph. So I'm going to use black to indicate the height of the black curve, y equals x. So I just drew this little line segment right here. And then I'm going to move it out of the way for a second. And then it looks like the blue graph is pretty close at this point. So I'll use blue right here. There it is. So graphical addition says if you want to know where the y coordinate of the sum of these two graphs is, you just add those two line segments. So that's what I'm going to do right here. I'm going to take this black line segment and I'm going to add it on top of the blue one. And then I should end up with a point right here. So that's where the sum of x and sine of x will lie. And I'm going to go through and just do that for a few points. So here we go. Let me do this one. How about we do, oh, here, I'll do this. How about we go to this spot right here? There we go. Draw that blue line. And then draw this black line in the same spot. Okay, and then I'm going to add those together right there. So now I have a new point. There we go. Now let me go over a little bit. Actually, I'll leave that one there. Let me go over a little bit to, how about we go right here? Okay, and then I'm going to add this length right here, the black length. And if I add those two things together, I get this. So I've got another new point right here. Okay, I'm just gonna go through and do a few of these. Oops, wrong color. Maybe I'll do this one, and then this one. Okay, add those together, make a new point. Okay, maybe I'll do, okay, how about I go over here? Let me do this one. So look at this. Now, notice the blue line here. The vertical displacement here is negative. So this is a negative value that we're going to take away from the black line. So let's do the black right here. Whoa, getting kind of tall. There we go. So there's the black line, but what I need to do is I need to take away the height of the blue line, take away the height of the blue line. So what I'm actually going to do is just move it down like this. I'm going to cover the blue line down here, and then I get a new point right here. There we go. And then I'm going to keep going along. So where's the blue? Here's the blue. The displacement is negative again, so I'm going to have to subtract. Here's the black. There we go. And now since there's a negative value involved, I need to subtract the blue from the black. Oh, wait, sorry, my mistake. Let's try that again. Here's the black. Something along those lines. Okay, and then I'm going to subtract the blue from the black, and I get this. Draw a new point here. And then I'm going to keep moving along. Let me do another one over here. Okay, there's the blue. Here's the black. See if I can do this. Ah, almost. I'll do it this way. Pretty close. Okay. Now I'm going to subtract the blue from the black, so I can just move this down a little bit. I get another point right here. And then maybe I'll do one more right here. So look at this spot right here, right at 2 pi. Right at 2 pi. There's no vertical displacement for the blue curve, but there is for the black curve. So let me do the black curve here. It'll be right, oops, like right about here. There we go. So now I've got a new point right here. And now we can connect the dots. So what does the sum look like? What does h of x look like? It looks like if you were to connect all these dots in a smooth, continuous curve, like so. So this is h of x equals x plus sine of x. Pretty cool, huh? That's how you do it. So again, you can do this with any function. Oh, I realize you can't see that. There we go. You can do this with any function, the sum of any two functions. You can interpret it this way. That's exactly what I'm saying. And you can also go backward. You can start with a sum and start decomposing them by subtracting, right? That's something that we're going to talk a little bit about at the end here. But let's see how ours compares with what the book gave. Oh, pretty good, right? Pretty good. Check it out. There it is. Cool stuff, I think. So That is an example of graphical addition. So this is just like x and sine of x. We added those two things together, and this is what we got. All right, now let's try a more interesting example. So here, let's graph the function f of x equals sine of x plus cosine of 2x. And this is another one where I'm going to spend a decent amount of time doing it, but I want you to try this one on your own at home. So think about it for a minute. All right, now say something out loud to yourself about how you would start. How do you think you would start this problem? All right, now try to work it out on your own. Draw some nice graphs. That's the first thing I'd recommend is draw a nice graph of sine of x and a nice graph of cosine of 2x on the same plane, and then see if you can do the graphical addition just like I did. And we'll do it together in a moment. All right, here we go. If you want, you're more than welcome to fast forward and skip if you don't want to see this, or you can look at the next slide. The next slide has the solution on it. Uh, Screen's copping out on me. But I'm going to try to do this one pretty carefully with a lot of accuracy. And the first step is to graph sine and cosine of 2x. So let me start by drawing some axes. I'm just going to do one period. Here we go. Give myself some space. So we'll say this is x, this is y. I'll set this to be 1. Or actually, you know what? I'm going to need some more space. So I'll set that to be 2, that to be 1, -1, -2. Okay, and then I'll put 2 pi way out here. Remember when we graph these functions, if you want to graph one period, you graph 2 pi, and then you divide that period up into 4 equal-sized pieces, and so on and so on. We're just going to do that again. So right in the middle, we've got pi. Right in the middle, we've got pi over 2, 3 pi over 2. So we can draw the sine curve. Maybe I'll do the sine curve in, oh, let's use green. So sine goes like this. Maybe I'll move this up here. There we go. So the sine curve looks a little bit like this. Something like that. Now I need to draw a cosine of 2x. So remember here, maybe I'll use blue for this one. Remember for cosine of 2x, the period is going to be affected, right? So because there's a scaling factor, there's an omega there that's not equal to 1, that's going to change the period. And if you remember from when we did this before, the way this is going to change the period is it's going to shrink it. So now we're going to run through those inputs twice as fast. So the period is going to be twice as short, which means the period of cosine of 2x is pi. So we're going to get a full period of cosine of 2x, a full period of cosine 2x on the first half of this interval, so from 0 to pi. So I'm actually going to put some other intermediate points here. These are the fourths of pi, and then I'm going to connect these dots. Okay, so cosine starts here at 1, goes down, goes down. Actually, let me move this one too. Right? Okay, goes down to here, back up to here, back up to here, and then repeats. Oh, I forgot to draw the other ones. Dash, dash, down, down, up, up. Okay, so cosine of 2x looks a bit like this, like so. Maybe I'll move this point a little bit just to make it a little clearer. There we go. So now we've got our two curves. We've got cosine 2x, we've got sine of x. Now we're going to do graphical addition, and we're just going to add these together. So how I'll do this, I'll stick with blue and green. Okay, so for the first spot, I'll start at 0, and maybe I'll just add all the critical numbers here, or all the points of interest, I should say. So here first, I gotta highlight these, I'm gonna mess these up. Sine of x and cosine of 2x. There we go. All right, so at 0, sine of x has no vertical displacement whatsoever, but cosine has some. So we will get something that looks like this, right? And then when we add them together, we're just going to get a new point here in red. I'll call the sum f of x red. All right, now let's move along. So what about right here? Right here at this point, there's no vertical displacement from cosine of 2x, but there is some vertical displacement from sine of x. So we're going to get another point right there on this curve, in fact. There we go. Now let's look at the next one. So here we're going to have some vertical displacement for cosine of 2x, but it's going to be negative. And then we're going to have some vertical displacement from sine of x as well, but it's going to be positive. And in fact, they're going to be exact opposites of each other. So what we're going to get is a point right here. And then we can kind of move along. I think what I'm going to do now is this, just to save myself a bit of time. I think what I'll do is, okay, so if I look at this and this, I would have to move this down. So I'm going to get a little bit of height right about here. Here we go. And then I should get some more height right here. And then right here, I'll have to double this height. So it'll go up, and I'll get something right about there. Let's see, right here, the displacement will be that. So I'm going to end up with this right here. Then if I move over a little bit, if I look at this one, I've got some negative displacement down here, positive displacement there. Oops. So then this is going to be like about there. And we can keep going along. Something like this. So you can kind of get the idea, but that's really what you do. And you can spend as much time as you want on it. That's pretty much just the same idea. So let me show what the picture will look like. Boom, there it is. There it is. So see, I should have gone a little bit farther, but that's okay. And it makes sense because over here in this region, right here, you're going to double the negative vertical displacement, right? So then you're going to go way farther down. That's what's happening over here. In fact, yeah, let me look at this right here. There's two instances of negative vertical displacement. So at this spot, come here, there we go. It's going to be a little bit lower. So this would be like down here. And we could have seen that with our graph if I had kept going. There we go. And that's it. So like that's graphical addition. That's graphical addition. I highly encourage you to try to do this with any sum of functions you've ever seen ever in your life, and just play with it sometimes and think about how that affects the graph. This can give you a lot of intuition for what these things should look like or what their behavior should be, because you'll see all sorts of functions, right? What if I give you a function that looks like f of x equals 3x plus sine of x? Well, now you have the skills to graph this function and this function. And so you have the skills to get a rough idea of what that graph would look like. You really, really do. You have the ability to see roughly what that'll look like. In this case, it's going to look pretty similar to this one. It'll look similar to that one, in fact. And these are the types of functions that you'll explore in Calc 1 and Calc 2 and so on and so on. Forever, right? Any functions you want to explore, you can do this stuff with. All right. Now, so, before I ramble too much, I'd rather ramble about something here. So what is coming on the mathematical horizon? So one of the reasons I wanted to go through this section in a little more detail is that this stuff is kind of giving you the foundations for something that's called Fourier analysis. And some of you are going to take a course in Fourier analysis later. It's a really, really fascinating course. And the applications of Fourier analysis are just everywhere, everywhere. Um, I had a friend who graduated a couple years before me from my master's program, and he got a job at Northrop Grumman, right? He just wanted to do applied math. And when I met with him like a year later, I was like, what do you do there? Like, how do you actually use your degree? And he was like, oh, it's really a lot of Fourier analysis and it's a lot of signal processing. Because, like we just saw, when you add two waves, That is the sound produced by the individual tones, right? So if you have a single tone and another single tone and you add them together, that's the sound that's produced when they're played at the same time. So a really important question and a really fascinating question is, how do you go backward? So if you've got a sound that plays, could you go backward and decompose that sound wave into a sum of individual waves where each individual is like a fundamental frequency? Or has a fundamental frequency. That's the idea. So how do you go backward? That's what Fourier analysis lets you do. That's what Fourier analysis lets you do. And graphically, it's reversing what we just did today. So imagine you started, imagine you started with the pink graph and you wanted to go backward, decompose that into a sum of two functions. That's what you can do with Fourier analysis. And it's got applications everywhere. Signal processing, image processing, like even image compression. If you want to know how images are compressed, like JPEGs, they use Fourier analysis to do that. They use Fourier analysis to do that. It's like backtracking from the data, and then you can always recover the data later when you do, well, when you do a Fourier transform. That's the idea. You can use it in crystallography, sonar, and more. It doesn't even have to be a physical application. It can be a purely abstract mathematical application. So, um, hopefully that gets you a little bit excited for things. But that's it. That's it. So now you should go try to do the homework. If you want, you can rewatch the lecture, look through the slides. But that's it for this section. I was really happy to explain simple harmonic motion to you all and hopefully get your interest piqued a little bit about some big ideas. All right. So I'll end it here. Thanks for listening, and I'll see you next time.